Hello, good morning. In the previous class, we are completing the Poisson's ratio and the relation between the Poisson's ratio in terms of expression for the Poisson's ratio in terms of elastic constant, that is alpha, beta and sigma. So in the today's class, we are continuing the relation between the elastic constant. There are three elastic constant. First one is the Young's modulus, that is determined by the Y, capital Y. Second is the bulk modulus, denoted by the letter K, and third one is the modulus of rigidity. So it is denoted by the letter neta. So we have the four relations between these three constant, that is Y, K and neta and sigma. So different types of relation introduced in our chapter. So in that we are first continuing the relation between the Y, K and neta. Relation between Y, that is Young's modulus, K, that is bulk modulus, and third one is the sigma, that is the Poisson's ratio, and assuming the expression for the volume strain in terms of alpha and beta. Okay, so in that expression we are directly assume that the volume strain we have volumetric strain, that is denoted by the 3 alpha minus twice beta into P. So we have to use this relation, that is volume strain is equals to 3 alpha minus twice beta into P directly in that expressions. There is no any need to calculate this type of relation by using long method. So it is not our work. So that's why we are directly use this equation, volume strain equals to 3 alpha minus twice beta into P, and we have to introduce the relation between the Y, K and sigma. Here Y is the Young's modulus, K is the bulk modulus and sigma is the Poisson's ratio. So for that, by using the definition of bulk modulus of elasticity, that means K is equals to, bulk modulus is denoted by the letter K, K is equals to volume stress divided by volume strain. And in that volume stress we can write as a compressive stress or we can write extensional stress. Okay, compressive or the extensional stress divided by volume strain. We know that volume stress means the force per unit area, and in that case force per unit area is nothing but the pressure. So that's why we write here volume stress means P divided by, and volume stress we write here equation 3 alpha minus twice beta into P. Okay, here K is equals to P 3 alpha minus twice beta into P. So we are cutting this P, so we get K is equals to 1 divided by 3 alpha minus twice beta. Okay, so this is the half relation. So from that we are taking cross multiplication, 3K alpha minus twice beta is equals to 1. Okay, by doing cross multiplication, 3K alpha minus twice beta is equals to 1. So dividing this equation by alpha, dividing this equation by alpha both side. On both side we get here 3K alpha minus twice beta divided by alpha is equals to 1 by alpha. Okay, so here 3K outside the bracket, there is no need to divide. Here in the bracket we get 3K alpha divided by alpha means 1 minus twice beta divided by alpha is equals to 1 by alpha. Okay, So we know that by using the Poisson's ratio we derive two equations. That is, first one is b by alpha, beta by alpha. This is nothing but the Poisson's ratio sigma. Poisson's ratio sigma. Okay, means b by alpha is equals to Poisson's ratio sigma, which we already derived in the previous class, and 1 by alpha, and here 1 by alpha is equals to Young's modulus. Young's modulus, that is y. So put this equation in that form. That is, here 1 by alpha is nothing but the y, and this beta by alpha is nothing but the Poisson's ratio. So we get 3k 1 minus twice here beta by alpha, putting here sigma, is equals to, and 1 by alpha is nothing but the y. So therefore we can write y is equals to 3k 1 minus twice sigma. So this is the relation between the y, k and sigma. Okay. So then next is the y is equals to 3k 1 minus twice sigma. So next relation is the relation between y, neta and sigma. Relation between y, neta and sigma. Relation between y, neta, that is modulus of rigidity, and sigma. Here we have assuming the shear strain. So we have shear strain as a direct formula is equals to, that is denoted by the letter theta. Theta is equals to twice alpha plus beta p. Twice alpha plus beta into p. Okay. So we have to derive the relation between y, neta and sigma. So that's why by using the definition of rigidity of modulus, means by definition of modulus of rigidity, that is neta is equals to shear stress divided by shear strain. Here neta is equals to, we know that shear stress is equals to, shear stress is nothing but the, here also shear stress has the formula which we derived already in the previous classes, that is, here also use we P, because this is nothing but the force per unit area, and shear strain is nothing but the twice alpha plus beta into P. So cancel P, we get twice neta. By using cross multiplication we get twice neta, alpha plus beta is equals to 1. Again dividing this equation by alpha, dividing equation by alpha, so we get twice neta alpha plus beta divided by alpha is equals to 1 divided by alpha. Then twice neta, here alpha divided by alpha matlab 1 plus beta by alpha is equals to 1 by alpha. So by using the constant, that is again 1 by alpha is nothing but the y, and beta by alpha is nothing but the sigma. So use this relation, beta by alpha is equals to sigma. Here put the value beta by alpha is equals to sigma, and 1 by alpha is nothing but the y. So we get twice neta 1 plus sigma is equals to y, and y is equals to twice neta 1 plus sigma. So this is the required relation between the y, neta and sigma. These are the two equations which we already performed here. So by using this two equation, we can calculate another two equations in the next class. Thank you.